So, good morning, everyone. Welcome to the PhD defense of Miguel Altamirano Cabrera. We will go through the topics very soon. And my name is Clément Fortin. I'm a full professor and Dean of Education at Skoltech and professor in the Center for Digital Engineering. So, we will follow a procedure. I will introduce the jury members this morning and the candidate. And we'll have, the candidate will have a maximum of 40 minutes, approximately 40 minutes for his presentation. And then we will go through a question and answer from the jury member. We will start with the external member and then go around. And I will have the privilege of the last few questions. And then we'll have opportunity for questions from the audience in the room and in Zoom, if there are some. And then we'll have the word from the supervisor, Professor Tseteoku. And then we'll have closed deliberation of the jury members. And then we'll have the outcome announcement at the end. All right? So let's go with the first I guess yes, it's me, I guess. I've already said who I am. I arrived in April 2014, and between 2010 and 2014, I was president and CEO of a CRIAC, a Consortium for Research and Innovation in Aerospace in Quebec. And I had been, before this, a director in the Department of Mechanical Engineering at École Polytechnique of Montreal, and a professor at École Polytechnique since 1987. In around 2000, I created Polyplan Technology, a spin-off company of École Polytechnique, and the company developed an innovative PLM solution for concurrent engineering and manufacturing process planning, and it's known today as MPM Link, a component of PTC Windshield PLM platform. And I'm a fellow of the Canadian Academy of Engineering. It is my great pleasure to chair this jury with you this morning. Next, please. Professor André Somov is an associate professor at Skoltech, head of the Intelligence Sensing Group. He's joined Skoltech in 2017. He graduated from the Russian State Aviation Technological University, MATI, with an honors degree in electronics engineering. In 2006, Dr. Somov received his PhD in electronic engineering in 2009 from the University of Trento in Italy, having specialized in power management in wireless sensor networks under the supervision of Professor Roberto Passeroni. His research interests cover power management for wireless sensor networks, WSN, and Internet of Things devices. Cognitive IoT and associated proof of concept implementation are also in his interest and work. Dr. Somov has published more than 100 papers for peer-reviewed international journals and conferences. He has delivered a number of invited talks at Berkeley Wireless Research Center, Luxembourg, and also at Interdisciplinary Center of Nike. He has been general chair of the 6th International Conference on Sensor Systems and Software, the IoT 360 Summer School of the Internet of Things in 2014 and 2015. Andre holds some awards in the field of WSN and IoT, including the Google IoT Technology Research Award in 2016 and Best Paper Award of IEEE IOP in 2019. So, Professor Somov. Then, Professor David Navarro-Alasson from the Hong Kong Polytechnic University is an associate professor with the Department of Mechanical Engineering at that university and the principal investigator of the Robotics and Machine Intelligence Laboratory, OMI Lab. His research mostly focuses on modeling and control of robot motion tasks. The constant goal of his work has been the establishment of methodology that provide robots with advanced sensory motor capabilities. His research on sensor-based robotics has been supported by many competitive government funds and the Hong Kong industry, David is a senior member of the IEEE and serves as an associate editor of the IEEE Transaction on Robotics. In 2014, David received his PhD degree in mechanical and automation engineering from the Chinese University of Hong Kong, where he was supervised by the world-renowned scholar Professor Hun-Hui Liu and received the prestigious Konak CYT Fellowship during his doctoral studies. David worked from 2014 to 2017 at the CUHK T. Stone Robotics Institute, first as a postdoctoral fellow and then as a research assistant professor. He has had visiting position at the Technical University of Munich in Germany and the University of Toulon in France. Welcome, Professor Navarro Alarcon. The next one is Professor Wuchan Zhao from Tsinghua University. Dr. Wuchan Zhao is an associate professor and leader of the THU Soft Robotics Research Group in the Department of Mechanical Engineering. She joined the Tsinghua University in 2021, working previously at Harvard University as postdoctoral fellow with Professor Robert J. Wood. She received an MSc and PhD degrees in mechanical engineering from Cornell University, Ithaca, New York, in 2015 and 2017, respectively. Her research interests include soft robotics, soft sensors and actuators, bio-inspired robots, robotic manipulation and locomotion, and others. She has been selected as the Forbes China 30 Under 30 in 2018 and MIT Technology Review Innovators Under 35 China in 2020. She served as the associate editor for IEEE Conference on Soft Robotics in 2019 and 2020. Currently, she's an associate editor for IEEE Transaction on Robotics and the review editor for Frontiers in Robotics and AI. Welcome, Professor Zhao. Next, please, is Professor Tatiana Padlachikova from Skoltech. She's an associate professor and director of the Skoltech Center for Digital Engineering. She joined Skoltech in 2013, working previously in Royal Observatory of Belgium, Laboratory of Astrophysics in Marseille, and Space Research Institute of the Russian Academy of Sciences. Her scientific interests are related to solar and solar terrestrial physics, space weather. She developed a number of space weather services, including sunspot number, solar radio flux, and geomagnetic storm forecasting, prediction of arrival of high-speed solar wind stream at Earth. Dr. Padlachikova is a coordinator of the Skoltech Master Program Engineering System. She holds numerous awards, including the International Alexander Chichevsky Medal for Space Weather and Space Climate 2015, Belgium, Best Professor of the Year 2018, Mentoring, Best Professor of the Year 2019, Lecturing, and Best Professor of the Year 2020, Teaching Excellence at Skoltech. She got recognition for excellence in research, teaching, and impact and service to Skoltech and the wider community in 2022 and 2023. Welcome, Tatiana, to the jury. Okay, I think that's about it for the jury members. And now we have the supervisor, Professor Dimitri Tetsiroukou. He's associate professor for the Center of Digital Engineering at Skoltech and head of the Intelligent Space Robotics Laboratory. He received his PhD in Information Sciences and Technology from the University of Tokyo, Professor Susumu Tachi Laboratory in 2007. From 2007 to 2009, he was a GSPS postdoctoral fellow at the University of Tokyo. He worked as assistant professor at the Electronics Inspired Interdisciplinary Research Institute, Toyohashi University of Technology in Japan from 2010 to 2014. His research interests include autonomous robots, swarm of drones, human-robot interaction, wearable haptics and tactile display, teleexistence, affective haptics, virtual and augmented reality, and artificial intelligence. In 2023, he was awarded by Elsevier the rank of the top 2% of the world's most cited researchers. Dimitri received such prestigious awards as Best Paper Award, Asia Haptics 2022, finalist of Franklin V. Taylor Memorial Award, IEEE SMC 2021. Best Demonstration Award, ACM SIGGRAPH Asia 2019. Best Demonstration Award, Bronze Prize, Asia Haptics 218. Laval Virtual Awards, ACM SIGGRAPH 216, and the Best Paper Award of ACM Augmented Human in 2010. So, pleasure to have you with us, Dimitri, this morning for this very important event. Okay, next please, the PhD candidate now. Miguel Altamirano Cabrera is a PhD candidate and a junior research scientist at the Intelligent Space Robotics Laboratory in the Center of Digital Engineering at Skoltech. Miguel received an MSc degree in Space System Engineering from Skoltech in 2018. His research interests include collaborative robots, haptics, human-robot interaction, medical robots, wearable haptic and tactile display, virtual and augmented reality, and artificial intelligence. During his PhD studies, he published 3 journal papers, Q1, Q2, and 24 conference papers, peer-reviewed H-index greater than 10, in prestigious international conferences such as A-Star Core, in ACM IEEE International Conference on Human-Robot Interaction, HRI 2024, SIGGRAPH, Aerohaptics, etc. Miguel received prestigious awards such as finalist of the Franklin V. Taylor Memorial Award, IEEE SMC 2021, and the Best Demonstration Award, Bronze Prize, Asia Haptics 2018. So, I think that we are ready now for the presentation. You have 40 minutes to present, and we will listen to you very carefully. All yours.
Okay, good morning. Thank you very much for being here. Thank you for the committee this year too, the professors that are online connected. So I will start presenting my work. So my thesis is entitled Development of a Robotic Teleoperation System with Haptic Feedback for Dexterous and safe object manipulation in a remote environment. So let me start with some introduction of the work. I'm here, right? Okay. So as we know, the remote manipulation in the last years, the teleoperation of the robots has improved in many fields, no? From the medical robots to the space to the waste of nuclear waste in the industry. For example, here we can see how this doctor, or this medical doctor, is telemanipulating this Da Vinci robot. He's using this system to move the robot in another place and is inside of the human. So this implementation of teleoperation is very important for the development not only of the science but for the healthcare of the users. In the other hand, the development of haptics interfaces is very important too in the last years because it allows to the users, for example, here in the same example with the teleoperation of the robotic Da Vinci, to have the feedback in the hand of the doctor to arrive to the right position, to apply the right force, and to don't make any damage inside of the body of the users. So this is a very critical work that implementing haptic feedback, we can increase the immersion of the users and increase the safety for the people that is in this kind of systems. Another example of this is the Canadarm1 and Canadarm2 were installed in the International Space Station, and they were teleoperated from the ground. These robotic arms serve for many things, not like to assemble the space station, to grasp many rockets that are arriving to the space station, and to help the astronauts and cosmonauts to make some task in the International Space Station. The last version, Canadarm, will be located in the Moon Gateway and will help the people to explore the Moon in 2028. So the science is working, and science and technology, and many universities are working to develop these technologies for robotic systems, to use them and to implement this haptic feedback to give them more immersion during the teleoperation of the systems. Many works were developed in the last time, especially for the fingertips. For example, this work done by the university from TUM, from the Technical University of Munich, they developed this haptic feedback in the fingertips to give the information how these two robots are grasping and telemanipulating different objects. For example, here, the movement of the fingers is moving the robots in the remote environment, and after is receiving some haptic feedback in the fingers to locate and to telemanipulate in a better way. As you can see here, many haptic devices were implemented for the fingertips in the last time. Another positive thing from this work is the teleoperation by the finger position. If they move the fingers, the robots are moving the same way. And some other positive things from this research, this type of research, is that it has some sensors in the remote part. So the robots have these sensors that after communicate the information to the haptic feedback and to the user to operate in a better way. However, as I mentioned before, this system and many other systems, they implement haptic feedback only on the fingertips of the users. And in the robotic part, there is not collaboration with humans, so there is only some objects to manipulate. In the same way, many interfaces for teleoperation were developed. For example, this interface done by the MIT implement different pins which are moving according to the position of the hands in the local environment. The user is moving the hands, and after these pins are moving to make this interaction with the surfaces. The positive thing of this work is that this teleoperation is done by the position of the hands, are capturing by computer vision, and after the pins are moving to have this interaction. So we can have the possibility for bidirectional shape capturing and rendering, so to have some haptic feedback too from the users. However, this device is with a very small working area, so we can manipulate only these objects in this part, and it's a desktop haptic interface, so we cannot move on, we cannot wear it. There are many other applications of teleoperation. For example, in this work, you can see the operator that is wearing this glove, and with the movement of the hand, so this glove is reading the positions, and after is transforming these movements in the robotic hand. As you can see, when the user is moving the hand, the robotic arm is moving the same way. It has some optical mock-up, as you can see in the wrist. So the robot can move in the same way. Very positive from here is the tactile feedback. You can see here the operator is blind, so doesn't have any visual feedback, and only with the sense of the touch that receives in the fingertips, the user is capable of teleoperate the object. He can grasp and he can manipulate the object. Another positive thing from this research is that it has a lot of sensors, these hands. Now, in each finger, they have the arrays of sensors that transmit this information to the user that is teleoperating the object. However, as I mentioned before, this work is presenting only haptic feedback in the fingertips. No? And maybe in future I will explain you how we can implement it in another part of the body. And in the remote environment, the robot is moving only in an environment without humans close. So there is not some collision avoidance. In another research, people are making this teleoperation of the robots, but in the remote environment, there are some obstacles that are very important to have to avoid the collision. So for this works, the teleoperation is done by haptic systems, and after implements this collision avoidance algorithm. However, these type of devices are desktop and have only kinesthetic feedback. So we can see here from these works three principal parts. The first one of these is the implementation only of the haptic feedback in the fingertips of the users. There are only few applications of haptic feedback in different parts of the body. For example, in the forearm or in the back, in the feet. However, we need to continue exploring these parts of the haptic feedback to increase the immersion of the users, and because when we have some interaction with the objects, it's not only with the fingertips. No, all the body is making this interaction. In the other part, we need to explore more deeply the teleoperation interfaces. As you can see here, these teleoperation interfaces are implementing many hardware, many specific software, and after the communication is a bit difficult to implement. So we need to explore more that part and how we can give high quality tactile feedback in the users in different parts of the body. And in the third part, we can explore too the perception of the users in a human domain environment. So when we teleoperate the robot, how we can make some collision avoidance of the system to increase the safety of the users. So with this background, we arrive to three different questions, research questions. The first back is according to the haptic feedback. As I mentioned before, the haptic feedback provides many advantages. And many comprehensive research has done, especially for the fingertips. However, here we found some research gaps. For example, here, no technology for high-quality multi-contact interfaces for dexterous manipulation in remote environments. And no comprehensive research in the field of tactile perception in other parts of the body, for example, the palm, that we will concentrate in the future. So here, the research question number one was how to improve the design of effectiveness of haptic interfaces for the user's palm during teleoperation. And the novelty that we implement in the thesis, we present in the thesis, is the development of a study to explore the interaction of the palm with different surfaces and the design of a wearable multi-contact haptic interface for the palm. The second research question was focused in the user's immersion in teleoperation. So in the state of the art, as I mentioned before, we have this robotic telemanipulation, teleoperation that was central in the technological advances in the past decade, in the last years. And the cutaneous feedback presents a very promising solution to increase the immersion. So here we write to the research gaps, like there is small working areas for the motion capturing system to perform the teleoperation. As we see before, only in these small areas that the people can move the hands, maybe make the teleoperation, so we need to increase these motion capturing systems. And no technologies to allow the teleoperation without the implementation of extra hardware. So always, as we see before in the research background, they implement these big haptic devices and the specialized sensors. So here the research question number two was how we can improve the user immersion during teleoperation and remote object manipulation using haptic feedback. And here, as novelty, we develop a teleoperation interface based on hand gesture recognition through teleconference and implement haptic feedback on the palm during the telemanipulation. The research question number three was focused on the user safety during human-robot interaction. As we can see, the human domain environment, we can teleoperate the robots to take advantage and took benefit from the human dexterity and the precision of the robot. So we need to implement these systems where the users and the robot are working in the same environment. And most of the human interaction frameworks are using cameras, these optical passive technologies, for implement these user tracking. So here we write to these research gaps. We need to increase the safety of the users during the human-robot interaction, and no many research about the implementation of haptic feedback during human-robot interaction. So the research question is possible to improve the user safety during human-robot interaction in human domain by haptic feedback? So here, as novelty, we develop a framework to ensure the safety in the human-robot collaborative environment, and the system composing a haptic feedback display in the forearm of the users, a low-cost wearable motion capturing system, and a collision avoidance algorithm. The thesis structure was divided in 8 chapters. The first one was the introduction. The second, we talk about the background. The chapter number 3, we developed the haptic feedback for the palm. In the chapter number 4, we make a study about the tactile rendering of the information when we are grasping some objects to the palm of the users that is making the teleoperation. In the chapter number 5, we developed this teleoperation system based on a hand gesture interface through a teleconference system. In the chapter number 6, we implement the teleoperation system with haptic feedback in the palm of the users. the chapter number 7, we explored the human-robot interaction framework when we implemented the haptic feedback in the forearm of the users. And the chapter number 8, we present the conclusions as future work. Here you can see the thesis structure, how the chapter number 3 is after complementing the chapter number 4, and together with chapter number 5, we have the system integration in chapter number 6. So let's start with the chapter. In chapter number 3, we developed this haptic interface for the palm. To develop this haptic interface, the first thing we did was the implementation of an array of sensors in the palm of the users and implement this investigation during the interaction with different surfaces. We implemented 4 different surfaces. So the first one was 65 diameter of a sphere, 130 millimeters of the diameter, and 240 millimeters. And the last one was a flat surface. So we put this array of sensors in the palm of the users, and after we asked the users to make some interaction with these surfaces. During this interaction, we were saving the force that we are pressing the object, we are making this interaction with the objects, and what are the points and the quantity of the force that we apply in each point of the 15 sensors in the palm. This research we implemented, we did using 10 participants from 21 to 30 years old. You can see here are the results of the result. In this graph, we show the number of the points that are activating according to the different forces and different surfaces. For example, here the number A is the small sphere, the 16.5 millimeters, and you can see how the points are interacting more in the center of the palm. So they are activating more points according to more force that we are using in the palm. The same for big interfaces. So these results can help us to develop new haptic displays with multi-contact interfaces to implement these realistic sensations in the palm. Not only like to give some points, but to implement the real sensations when we are in a remote environment or in virtual reality. After that, we have the development of the haptic interface. We developed this device we call Link Light. It's a multi-contact tactile feedback based in the inverted fiber linkage mechanism. As you can see, we have 2 servo motors in the part, and after 5 inverse fiber linkage mechanism that provides 3 contact points in the palm of the users. The rotation of these servo motors calculates the position of this contact point, so in X and Y position. So we can see here, we developed the kinematics of the system, and we found the alpha, the angle theta in the position A and position E. These two angles are giving the XY position. So here we can program different sensations, different patterns in the palm using the inverse kinematics. We have only the XY position of each of the 3 contact points, and we can make this, provide this sensation in the palm. This is the structure of the device. We have these 6 servo motors, 2 for each one of the independent contact points. We implemented some force sensors in the contact point, and in this case, we use this HTC tracker to locate the hand in virtual reality. After we designed different patterns to explore how the users can recognize this pattern or how they can make this sensitivity in the palm. So we designed 11 tactile patterns with different positions of the contact points and asked 16 volunteers to make this study to study the tactile perception of these 11 patterns. You can see here this confusion matrix is presenting how they can recognize the different patterns. The average recognition rate was 78.1% with the 11 patterns, and you can see here pattern number 4 and pattern number 6 were the patterns that are presenting more, so the highest recognition rates of 91.3%. You can see here the 4 pattern is giving these 3 points in these positions, as you can see here in the top, and the pattern number 6 is giving 2 points in the back of the palm. In chapter number 4, we presented the system that we implemented, how we can render the tactile interaction when we are making the telemanipulation of some soft objects, for example, some pipettes. For this work, we implemented this system. We had the robotic arm, the robotic gripper, and we implemented two arrays of sensors, 10 by 10, so 200 points in each of the fingers in the gripper. So when we start to grasp different objects, we make this data set in different positions and different angles of the grasping the pipettes. We design this pipette holder. We can put the pipettes in different positions, and after we create this data set. So how the robot is closing, filling with the sensors, to after design some commercial neural network with artificial intelligence to have as output the position and orientation of the grasping the pipettes. We implemented 4 different angles, 90, 45, 135, and 0 degrees. We did 3 different positions, and we consider 31 positions of the closing the gripper. So in this we have a big data set, and we can see here the demonstration of how we can grasping the pipettes, how the sensors are activating. This is a very high quality information that we used before to create the mask when we are making the telemanipulation, and to give this mask to the users when they are making the manipulation of the pipettes. So here, as output of our system, we had these 11 patterns that we transform from the telemanipulation of the object, so how we are grasping the pipettes, to the tactile information in the palm. According to the output of the CNN algorithm, we give the different positions in the palm of the users. For example, here, if we have 90 degrees in the center of the fingers of the gripper, we give this pattern in the center with the different forces, according to the press, the force that we put in the device. We make some study for these two, so we ask 10 participants to make the telemanipulation, one implementing the masking of the patterns in the hand, and other implementing the patterns in the palm of the users. As you can see, the overall recognition rate, only applying the raw data to the haptic interface, was very low, was 9.67%. And with the mask, we increased this recognition rate to 82.5%. And the recognition time was faster, 3.1 seconds. In the chapter number 5, we implement the. In chapter number 5, we were working in the time of COVID, no? So it was for us a bit difficult to come to the laboratory, and all the meetings that we had, it was like now, the defense through Zoom. So we were thinking how we can make this interaction and to implement some teleoperation system using the same interaction that we have with humans in this moment that was through Zoom, to these teleconferencing systems. So we came to the idea we can solve, because we didn't have many hardware to send to the houses, or the people that were, manipulating some very dangerous materials. We didn't have all the hardware or the software specific to make these tasks. So we were thinking how we can do it to make the same interaction, as I mentioned before. So we came out to this CNN-based hand gesture recognition interface to operate the collaborative robot using Zoom, using some teleconferencing systems. For example, this is the system that we implemented. So we have in one hand the camera of the camera of the user. After we implement some gesture recognition in the hand, and according to that gestures, we are teleoperating the robot. So we move to different positions, we open, close the gripper, and we change the orientation of the robot. This system is a multi-user system too, because here you can see these two guys that are teleoperating the robot in the same Zoom meeting. So we just change from one user to the other to start to make the teleoperation of the robotic system. For this task, we train 4 different gestures. So the one with number 1 in the hand, the rock and roll gesture, peace gesture, and no gesture in the hand. Using these gestures, we classify the gestures in the teleoperation system, and we start moving the robot in different ways. This teleoperation system was after compared with the baseline interfaces that are more used now in the market. That was the joystick from the controller, like the Logitech interface, and the teaching pendant of the robot. So these interfaces are the most used now, the most easy to implement in the teleoperation. So we make the comparison of the proposed system to these 2 most used interfaces to see how we can accept this interface or not. So we implemented the NASA TLX task load questionnaire, the system usability scale questionnaire, and the user experience questionnaire. The results that we achieved with our system propose that this interface is equivalent or surpassed in some parts of these baseline interfaces. In the next chapter, we integrate the haptic feedback and the teleoperation interface that we implemented in the previous chapter. Here, we make the user study implementing the system. In the remote side, we have the robotic, the cooperative robot with a gripper module which is embedded with the array of sensors that after is making the telemanipulation of the pipettes. We ask to the users to grasp the pipette, to take some water from the liquid container, and to put some drops of this liquid in the test cassette. In the local environment, we have different users that were implemented the teleoperation system with the gesture recognition in the right hand, and in the left hand, we are providing haptic feedback according to the position and grasping of the pipettes. The system integrates shared control teleoperation, we have some virtual buttons to predefine positions. So with the hand gesture recognition too, we press different buttons, the robot is going to different positions, as you can see here in the video. Here, Osama is teleoperating the robot with the hand. With the buttons, the robot is moving to different positions, and after in that positions, we have freedom to move the robot, to change the position, the orientation, and to open and close the gripper. So here you can see the buttons, how he is making this interaction with the robot. Here moves the robot in different positions. We close, and after the sensors are sensing how we are pressing the pipette, in what position, what orientation, and that information is rendered in the left hand of the user. Here you can see we can take the liquid with the pipette, we can interact with the liquid, we can probe the liquid, we can put, and after we move the robot to recreate one analysis of COVID, in this cassette test. So the robot moves, and after the user has the freedom to move and locate in the specific location according to the visual feedback and to put some drops. Here we can see that the time when we implemented haptic feedback than when we don't implement haptic feedback was reduced in 96.3%. So from 185.4 seconds to 146.8 seconds. And the same, the grip and opening position was much better when we implemented haptic feedback. So we open in the right position. So for the chapter number 7, we introduced the human-robot cooperative systems. So we are teleoperating the robot, but in the remote environment is a human domain environment. So here we have to study how we are safe we're guaranteeing the safety of the user that is making this interaction in the system. So here, as you can see, the user is in the same environment that the robot, and we implemented here the wearable haptic interface for the forearm of the users, the collision avoidance algorithm to make the collision avoidance between the robot and the user, and the tracker for the hand of the user. We use a wearable optical inertial motion capturing system. The haptic feedback that we implemented in the forearm of the users was according to different areas of the physical human-robot interaction. We distinguish these three different areas. The first one is when we have some distance with the robot, and we rendered some information in the forearm with the contact point. So according to the distance that we are closer or farther of the robot, as you can see here in the number A, we are moving the contact. So if we are closer to the robot, the point is coming closer to the wrists of the users. However, if we enter to the avoidance area, some vibration started to feel in the forearm of the users. So that makes the user understand that the collision avoidance algorithm from the robot is starting to work. And the last area was a critical area very close to the gripper, where we feel both of the vibration motors activate to alarm the user that you are too close to the robot is stopping, and we can take out the hand to avoid any collision and any damage to the users. Here you can see there is this collaborative task when the operator, so me, I'm working in the same environment as the robot. The robot is grasping different cubes, and after the user, we are making some task with the Lego cubes to measure after the pins and to collaborate with the robot. So you can see here the haptic interface is activated when the robot is closer to the hand. That alerts the user and take out the hand. So in this case, we achieve this, the minimal distance, so the distance that we are close to the robot increased when we apply haptic feedback by 33.9%, and the time for all the activity reduced in 46.3%. So here you can see in the first part is the robot moving alone, so without the presence of some user, so not collision avoidance activated. The second one, we don't have haptic feedback, so the collision avoidance is activated in many parts of the operation. So the time of the operation increased till 100 more or less. And in the last part, we implemented the haptic feedback. So here, when the activation of the collision avoidance algorithm started, the user was informed and the hand of the user can be taken out. So with this system, we achieve the decrease of the time by 46.3%. So in the last chapter, we presented the conclusions of our work. The first one is about the haptic feedback. So the first research question was how to improve the design and effectiveness of haptic interfaces for the user's palm during interoperation. So as first, we developed a novel method to investigate the sensation rate on the user's palm during the interaction with different surfaces. We developed the multi-contact wearable haptic interface for the palm, Link Light. We validate with the user pattern perception with average recognition of 78.1%. We introduced the CNN-based detection of tilt and angle position of the gripper while grasping the formal objects, and the user's perception during this grasping has the overall recognition of 82.5%. Here we have some limitations. The first one, that the haptic device was not tested in a multimodal interface. So we were given only the contact point, the force at these three independent contact points. And as future work, we want to implement the haptic feedback based on impedance control for different stiffnesses when we are grasping some different objects. So the force control can give the sensation of stiffness according to the impedance control. We move forward, the user immersion in teleoperation. So the second research question was how we can improve the user's immersion during teleoperation and remote object manipulation using haptic feedback. Here, as first, we develop a teleoperation interface based on CNN gesture recognition through video teleconference system. The results achieved the proposed system are equivalent or surpass the baseline interfaces. As third point, the teleoperation task was performed by the proposed system with and without haptic feedback on the palm while grasping the pipette, taking liquid and pouring some drops. And the results of the conversion time with the haptic feedback was reduced in 26.3%. Here we have some limitations to in the work. The latency of the interface was not considered in this study. And at the second, we consider only one hand to have the haptic feedback, and the other hand to make the interaction with the gesture recognition. So as future work, we want to implement this teleoperation with manual systems. So we want to study how we can have the haptic feedback and the gestures, because we will use both of the hands. And after, we want to explore different gestures using with the entire body of the users. As conclusion number 3, so about the user safety during human-robot interaction, the research question number 3 was, is possible to improve the user safety during human-robot interaction in human domain with haptic feedback? So in this part, we developed a human-robot collaborative framework which features a wearable multimodal haptic display, reset light, in the forearm of the users, and the wearable optical motion capture system. We implement the collision avoidance method, and after experimental results revealed that the active time of the collision avoidance algorithm is reduced in 46.3% with haptic feedback, and the minimum average distance between the robot and the user increased by 33.9%. One limitation of the system is that we use only one point of the tracking of the users, only the hand in this work. So as future work, we want to explore different motion capture system methods to track all the body of the users and develop a collision avoidance algorithm for the body of the robot. So till here with the conclusions. Now let me talk about the main achievements of this work. I achieved the H-index 7 with the publications that I have in Google Scholar and in Scopus H-index 5. I was honored to receive the Best Demonstration Award in Asia Haptics with the presentation of the haptic interface for the palm. I presented this device too in one of the most prestigious conferences, SIGGRAPH 2019, with only a few laboratories presenting this work, around 10 laboratories in this international conference in US. And I published the International Human-Robot Interaction, is one of the best journals for human-robot interaction, when I presented this CNN gesture interface for telemanipulation of the robots. I achieved 3 journal publications and some conference proceedings publications with peer review. So in total, we're 24. So I want to thank you for attending the thesis. I want to thank to the professor Dmitry Teterokov for all the support, all the time. Like, he was there to support and to encourage and to give all this needs improvement to have all this success. To all the master students that pass from my team in the Cobot Haptics team in the robot laboratory. It was very nice to see all of them passing and now being very successful in their careers. I want to thank to all the members of the Intelligent Space Robotics Laboratory, all the master students, PhD students, and all the volunteers that participate in the experiments at the SM Skoltech to give me the opportunity to make the research in this institution. So thank you for your attention, and let's start with the questions and answering session.
Okay, thank you very much for the presentation. It's now time to go to question and answer period. And we will start with our external jury members. So we will start with Professor Navarro Alasson from the Hong Kong Polytechnic University. Professor Alasson, please go ahead.
Thank you. Thanks so much. Maybe just testing. Can everyone hear me well?
Yes, we can hear you well.
I can see myself on the screen. All right. So yeah, thanks so much to Dimitri. Thanks so much to Miguel, and everyone involved in this thesis for inviting me. Very ceremonial. First time I see a Russian PhD defense. Very nice work. So maybe just to keep it brief and respect everyone's time, I have some very general questions. I don't I don't work on haptics. I mean, if I have to label myself in some way. I have here jotted a few things. So I mean, well, judging from the manuscript, I can see that the thesis is not. There's so many types of PhD thesis. The very broad area of robotics and sensing. This one in particular is not focused on purely mathematical or theoretical aspect. It has a very clear technological engineering focus on it. So there are things that Miguel has been developing and working on. So here we can see from the document, he worked a lot on electronics. He worked on actual prototyping of interfaces. There's a lot of software development. I mean, these experiments that he's doing, the interfacing with, I don't really know what software he used for video conferencing, but interfacing with, let's say, Zoom and controlling a robot, that's not something trivial. So I presume he spent many years or months doing this development. He did a lot of experiments on several of these devices and methods he developed. Also very nice that I appreciate, there were a lot of performance comparisons with human subjects. That's also very nice compliment. Another interesting and valuable, I'll say, because I mean, when managing a team, at some point one is responsible. Well, not entirely responsible. It is also important that once they finish, what are they going to do? In the case of Miguel, he has worked a lot on many technologies. So he has this nice mix that allows him to work if he decides that, to do it in industry. With some type of work, once we bring them, they are destined for academia. In his case, he has a broad spectrum of choices that he can do if he's granted a PhD degree. So maybe some information, some very general question, Miguel. So to more generally judge the work that you've done, so roughly how many years did you work for your PhD?
So this research is finished almost 1 year ago. So I was working for 4 years for this work.
Oh, wow. So this is a 4-year PhD work, the one you're presenting today, yeah?
Yes.
Okay, nice. It's, I mean, pretty standard. So maybe some more specific technical questions. So if I get right, based on your presentation, so you have a robot. I mean, it mostly follows, I mean, not to put it in a bad light, but a mostly traditional setup for sensing side of the robot and teleoperating with some form of feedback. So on the side of the human, the tactile feedback that you have some form of tactile feedback. You developed an interface, I believe is around page 10. Maybe would you mind putting, I still see my gigantic face. Would you mind putting maybe the slides regarding your work, page number 10? Yes, so if you can go page 10, I believe there was some design of your interface. This is 10. Yes. So, all right. So this is the device you design, you prototype, and that you're using to provide some form of haptile sensation to the human that is teleoperating the robot. Yes.
Yes.
Okay. Maybe here's my question. Also correct me if I'm wrong. This I don't work in a haptics, but every time I see this interface, this wearable interface, so bulky. I mean, not just yours. I mean, it seems to be the at least until this point, the common for most people, like very bulky. So for this interface, you only have 3 contact points, so 3 points where you can render some form of feedback into the human, correct?
Yes. 3 points.
So yes, so I don't know, within my very uneducated understanding of this. So it seems to me like a very drastic reduction on the amount of the resolution, tactile resolution that the human can have, right? So I mean, I mostly work with cameras. So, I don't know, I try to make an analogy. This will somehow be equivalent to providing a human some glasses and providing, I don't know, like 4x4 matrix of pixels, whereas our biological visual system can perceive much more, but we are reduced to only this very discretized form of information, right? So maybe my question, so I don't know, is there any, I don't know, design rationale that you follow or that you use for only considering these 3 points in the palm, or is this the current state of the art? Or I don't know if you can elaborate on this aspect. I would appreciate.
Yeah, thank you very much for your question. Yes, you are right. It's a bit big, the device. No, however, the design of this device is covering all the hand, all the palm. Sorry, all the palm of the user. So the 3 contact points are not static. So we can move in all the surfaces of the palm, or we can generate different illusions, for example, or having different objects in the palm.
Do you have a video of that? That helps for those that didn't do the work and are in the position of judging. Do you have any video of such?
Yes, let me
Just imagine that. I mean, where we can see the motion of those 3 contact points.
Sorry. Can you please play the video? So this video was a video that we used to present in SIGGRAPH. So here we presented the haptic interface in the palm. So the introduction we did is that we have to develop these haptic interfaces because the interaction with many objects are in the palm, not only in the fingertips. So for that we need to make this interaction with the three different points. So here is one version of the device that the user was wearing. The base is moving a bit to be more comfortable to the users to wear. And after these points are giving the sensation, in this work we were giving the sensation in virtual reality. No? So how the users can interact with different points in the palm. A bit further can give the movement. Yeah, so these 3 points are sliding in the palm, can give different positions according to the movement of the servo motors. No? So here is how is
I now get why you call it glide, right? So it's not really the 3 points. Let's call it 3 bands.
Yes.
Where the point is well,
so we can make these three contact points, and we can slide too. No, we can slide with different points, covering almost all the palm of the users. Now here we can see how the points are moving to different locations.
So sorry, here, Miguel. So how many motors is 3 or 6?
So we have 6 motors.
Okay.
Each one of the contact points are moving according to 1 point. So we can give different locations, like XY location in the palm, no? Like we find 1 point, but after we can give different forces in each one of the points. So here, for example, in virtual reality, we implemented the pressing some different buttons, or to feel some animals in the palm. So here, according to the interaction with the objects, no? So we can slide in the palm, we can give 3D movement, etc.
Okay. Yeah, yeah. Okay. I now get it. Yes. So you've
To arrive to the final version too, we designed. So I was designing different versions of this system, no? So we implemented. So we were uh, making some. Maybe we have more contact points, but the links are bigger. So we arrived to the final solution that is more optimal to have the contact in more of the places with the lower space to cover in the device. No, however, I agree with you. In future, we should explore novel technologies to create new haptic devices. No, for example, I don't know, soft robotics that we can implement with more contact points in the palm, and yes, recreate some sensations. I can say that I was honored to receive the prize of the best demonstration award with this device because it was very novel in this conference to present this multi-contact interface on the palm of the users. No? So the exploration of this field is continuing. So it's like so this device was in that moment very novel, no, presenting some novelty in the system.
nice, nice. Oh, well, thanks so much.
Thank you.
Right. I have another. Yes, yes. So that's on the human side, which is somehow the focus of your work. On the robot side, there's also some. I did see somewhere some display of I don't know. I presume some form of capacitive or assistive sensors. I don't know somewhere. I think you showed some display you developed
Yes,
for
yes.
the robot arm. Maybe I'm a visual person. Let's go and see that one.
This,
Um,
this haptic interface too, right?
right. Yes. Okay. Yes. So on the gripper, you use some, I don't know, some standard commercial. These are commercial sensors. Yeah.
Sorry. Actually, the sensors that we implement, this one, right?
Mm. Yeah. Are these commercial sensors? So is this something you developed?
No, it's actually because we had some collaboration with Professor Kajimoto Sensei. So he is developing these sensors in his laboratory, and because of this
Mm.
collaboration, we received these sensors. Are not commercial, are created by his laboratory in Japan.
Mm. Oh, right. Yeah. Okay. Yeah, so though it's not the focus of your work, but maybe, I mean, these are the questions I have, so I still ask you. So, I don't know, very, give or take 2, 3 years, this in the community, there's been a lot of interest on this new type of tactile sensors, not based on this technology, but using vision. This optical tactile sensors is basically a camera, a calibrated camera with information. So my question, have you considered using any of that? Would that, and if so, would that improve in any sense your methods, your approach?
Yes, actually, we're very interested in this type of sensors. We had some collaboration too with one center here in Escoltec that are developing these optical sensors, and we use for some work. However, we are in the laboratory. We don't have the technology in this moment to create these sensors, but these are very novel, very let's say smaller than these sensors, and the capabilities to implement in haptic rendering are yes very good. In future, I hope to have the opportunity to work in this field, yes, to
Yeah.
implement optical sensors. Yes.
Right. And I have another, say more on the work that I do. So even in the title, maybe can we go to the title of your thesis? Title, just first line, I presume. It's, development of a teleoperation system. So, yeah, my question is, even though I said that it's in my judgment is very much oriented into developing these six systems and devices, but I still wonder if have you during these 4 years developed any contribution, some fundamental contribution to the teleoperation methodology of this, being in the form of how you formulate or design or analyze or implement the teleoperation scheme by using, say, tactile feedback and having tactile feedback on the other side.
Yeah, thank you for the question. So the teleoperation system that we implemented was based in CNN gesture recognition. So for this teleoperation system, we are tracking the video of the user that is in the local site, and that gestures that are implemented by the hands of the users, we implement MediaPipe, one of the libraries from Google, and after that gestures, we train to recognize them. So the different gestures are equivalent to some operations in the robotic system. Actually, this work was presented in SIGGRAPH Asia 2019. And after that presentation of the work, Google and MediaPipe, they report our work as inspiration to their development. And after some years appear in MediaPipe, the gesture recognition. I'm not sure that it was because of our work, but I hope some inspiration we give to the MediaPipe research group.
Yeah, maybe my question goes, let's go to another visual aspect. You had a video where there's some student, I presume, wearing a VR device. I don't know if it's, say, from your group and using your device. Sorry, I missed that part. Maybe not. And that person is, no, it's blind. I think it's blind, and then holding some objects.
Yes.
Or any video of the actual teleoperation other than the one related to the Zoom. Yeah, this one. Okay, this one is, this one is not your.
No, it's not mine. No.
But do you have any experiments? I mean, these sort of, I don't know, I will call this is the teleoperation part. As opposed to identifying, I will call here a target, which I guess, or an action, which I guess is what the interface is doing. So do you actually teleoperate the whole motion of the robot based on, I don't know, something based on your motion?
Yes. I can show you, for example, this video. So in this work we are using Google Meets. So here 2 users are connected to the system, and the system is recognizing the gestures of their hands to move accordingly to the positions and the gestures that we have in hand. For example,
here's my. So where is the haptic part here?
Yes. So in this part of the work, we didn't implement some haptic feedback, but
yeah, we are referring to the title of the thesis. Is there any?
Yes. And in this video, here another operator, he is using the Zoom meeting tool and is wearing the haptic device in the left hand. Is receiving the information from the perception of the object that we are grasping. In this case, it's a pipette that we are grasping to take after the liquid and then pour some drops in the environment. So here we use the gestures of the hand to give this freedom movement of the robot, together with some specific locations that we send to the robot to make more stable the system. So here is everything by Osama that is making this teleoperation.
Oh. So the interface, or at least I mean, the focus, I mean, it's more like questions, clarifications that I have. So the part that you contribute, that you focus is on, through this interface, identifying what we wish the robot to do. How the robot do it is not in the focus of your work. So once is like move there, whatever that there means. And for a robot, it's actual numbers, and how it goes there, through what path, and with what other variables that's often are found in the teleoperation, the developing teleoperation schemes. That part you didn't focus on that. It's more on identifying the goal and what you want to do, and then if there's some contact, providing some feedback, right?
Yes, exactly. Mm-hmm.
Okay, so it's not like here's my hand moving and you have a tracker or something, and then there's another robot there following my motion. So you don't do this,
Yes,
right?
in this part of the work, according to the gestures that we have in the video, for example, if I put the gesture with one finger only, for example, I
Yes.
I announce to the robot to move in XY position. No? So
Sure.
according to the position of my hand in the screen, it's using like a joystick. So if you move to the left, the robot is moving to the left. If you move to the right, the robot is following the hand to the right. After, with another gesture, for example, the peace gesture, if I move to the top or to down, I am opening and closing the gripper. No? And the third gesture, for example, we implemented in this experiment was this like rock and roll. And after, if I move in different positions, I am changing the orientation of the robot.
Yes, and so for example, you select the active axis, like select X, and then the robot enables X, and then you select the amount of motion. Do you provide the amount of motion with this interface?
Yes, exactly. Mm-hmm. So we
Okay,
give.
then that's actually my question, because those are numbers that you're sending from somewhere into a robot. And how the robot reproduces this, you can formulate that. I mean, that's a very classical, let's say, problem in teleoperating systems. So have you like gone very much into the design of how you match this stream of numbers with the robot such that it has there's a term again, sorry, how is that called? Transparency? I forgot. It's like how fast and how stable it reacts to this stream of numbers of data on the other side, which might be in another continent or somewhere. I presume you did the experiments, I don't know, within the same city, and delay, maybe it's not model or include. So yeah, my question was, is there any work that you might or might not, you don't have to, done on the teleoperation methodology other than the interface?
Yes, so
I'm
actually,
not sure if I clearly
yeah,
framed the question. I apologize.
yes, thank you for the observations. They're very good ones and focused to my work. No, so the information that I passed from the robot to the user, from the user to the robot, sorry, it was as a joystick in the screen.
Yes.
So when I start to activate the gesture, this is the 0 position. And after, if I go down or up or down, left or right, this movement from the 0 position to the X or to the Y was translated to the robot to perform the same operation. Of course, implementing some control systems, no, like position controller, for example, to arrive to the right position, to not make some junky movements in the robotic area.
Okay.
So the teleoperation, I mean, the gesture recognition was done in the remote environments, and the environment where the robot is located. So we send the video only to the computer where the robot was connected, and after we make this translation of the gesture recognition and the numerical part of the position of the hand, and translating to the robot directly. So that's why, in that sense, we didn't face any delay. However, we want to study that part. In future, we want not only to use these gestures, but we want to track all the arm of the user and use the location and position of the arm to move directly the robot. No, if we move, for example, the shoulder, so the shoulder of the robot is moving in that way. However, it is some work that we are making this moment in the laboratory.
All right, thank you so much, Miguel. I have no more questions. I leave the room to the other examiners. Thanks so much. All right, cheers.
Okay, thank you very much, Professor Navarro Alarcon. I'm asking you, are you satisfied with the changes introduced by Miguel to your questions and comments?
Yes, yes, all
Yeah.
perfect. No worries.
Okay. Thank you very much. We will now go to our next jury member, Professor Uchan Zhao, for questions and comments. Please, Professor Zhao.
Hi, everyone. Can you hear me and see me well?
Well, we cannot see you now, but I guess we will as soon as we reduce the, yes, now we can see you well.
Okay, I can see myself as well. Okay, thank you for the invitation. And it's also my first time to attend a Russian PhD defense. It's very similar to the one that in my university. So basically, I have three questions, one as a specific technique question and two others as the general ones. Um, so, hi, Miguel. It's actually my second time to attend your presentation, and both are very inspiring. So my first question is regarding the device, the haptic device that you developed of the, I think it's a five bar mechanism, the mechanism. So my question is, when we really touch something, we feel a force exerted on our hand or palm, a normal force or shear force in some way. But when we wear a wearable device to render such a sensation, actually there is some reactive force, not only to the contacting point, but also from the reactive force from the device itself to other parts of the palm. And you understand what I mean? I'm wondering whether this reactive force is generating, what type of feeling are generating to the users? Are these reactive force make the users feel this feeling is not real? Actually, this question may be applied for all types of wearable rendering devices. I'm just wondering if it will generate a force feeling or so.
Hello. Yeah, thank you. Thank you very much for your questions, and it's a pleasure to see you again. Yes, this is a limitation actually for all the wearable devices. No, that we don't have any kinesthetic feedback. No, it means the feedback that we receive in the muscles, in the all the part of the body. For example, when we grasp something in the palm or in the tactile feedback, we receive some interaction, some texture, temperature in the skin, and after in the bones and in the muscles, tendons are reacting to the different weight, for example, no, of the environment that of the device or the objects that we are making some interaction to feel more realistic. No, so I can say that this is a limitation of the wearable interfaces. That maybe if we combine with another type of kinesthetic devices, we can improve the immersion of the users. Now here, the motors that we are implementing for the haptic device are very tiny. No, these servo motors generating only around 4 newtons in the contact points. So the movement that they generate, they don't make some perturbation of the users to feel another external part. However, I can mention, I should mention that I didn't study this part of the device. So maybe in future we can make a research, so user study too, to see how they feel this movement of the motors and make some like perturbances, no, in the perception of the users. Yes, thank you. Thank you.
Okay. Okay, thank you. My second question is, so based on your thesis, you have worked on different devices on different positions of our human body. For example, you mentioned about some fingertip sensation or haptic rendering in your literature review. And you yourself worked on the palm sensation rendering. And the safety, the last part of your work focused on the forearm of the skin. So can you compare different parts of our human body, which are more suitable to do what kind of rendering or haptic feedback, and some other differences these different parts are generating,
Yes.
something like their comparison.
Great, thank you for the question. Yeah, so many devices were developed for the fingertips, because in the fingertips, the amount of receptors is much larger than in other parts of
Yes.
the body. No? However, the number of the terminals in the palm of the users is very high too. We should, so, and because of the area, no? We have a bigger area in the palm than in the fingertips. So to arrive to of the numbers of receptors that we have in the palm, we should make the interaction or the perception in all of the fingertips of the hand. No? So the area that we have in the palm is equivalent in the receptors that all of the fingertips. So that's why we focus in this time in the palm. However, it was to open this part of the study, not to give the haptic feedback in the palm and not only in the fingertips. I agree that in future the haptic interfaces, they have to integrate the fingertips, the palm, and other parts of the body at the same time. No, but this is going to be like in the future work. In my work too, I make some development of systems for the fingertips too. No, the same fiber invert linkage system we implement in the fingertips to give the same sensation. After one limitation that we had when we are in this human-robot interaction environment, so the robot and the user in the same environment, it was that the user has to use the hands to make some activities.
Yeah.
So that's why we implemented the haptic feedback in the forearm of the user.
Yeah.
So that's what the principal reason, no, because we are using the hands, we cannot receive in other part.
Yes.
Yes, so basically it was.
And that's also my feeling. So our hands are so dexterous and so sensitive that we wanted to do everything. We wanted to do remote control and we wanted to feel the haptic forces. But adding some devices further on these hand will impede the hand to do dexterous work. So perhaps in future we need to investigate other places of our human body to achieve this haptic feedback. Okay, so my last question is, what do you think, if we are going to develop some future haptic devices, what do you think the bottleneck at this moment? Do you think it's like as David mentioned, the bulky size, or is the density too low, or some other characters you think is a bottleneck to make this technology more useful?
Yeah, so I think in future, I hope the size of the devices will decrease according to the implementation of new technologies. No? So I can say that some technologies that, for example, you're developing in your laboratory are very impressive, very small, and we can implement in the development of different haptic interfaces for different parts of the body. So I hope for in the future for commercial haptic interfaces has to be, of course, smaller and more wearable for the users and more easy to use. No, but this is like I hope to continue working in this field to develop these interfaces. No, but this not only focusing one part of the body, but as I mentioned before, as you mentioned before too, to explore different parts of the body, and maybe some other parts are very good to receive some haptic feedback. For example, for the people that doesn't have the hands, that they have some accident, they lost the hands, the sensations that they receive from the prosthesis that has some sensors are most of the times in the arms or in the back of the users. So to explore the sensations after is a field of research that is for me very exciting, and to continue working in that.
Okay, thank you. So that's all my question.
Thank you very much, Dr. Zhao. Are you satisfied with the changes and the comments that you received from Miguel? The thesis?
Yes, I have read the responses for my reviews, and I'm satisfied with them. Thank you.
Okay, thank you very much. We'll now go to Professor Andrei Somov for his comments and question. Please, Andrei, Professor Somov.
Yeah, Miguel, thank you for your work, for your research. Well, basically, I have two minor comments, questions. So the first one is whether you, maybe I missed it. So did you collaborate with doctors, maybe neurologists, on how to position sensors on the hand? Because we have similar projects and we, we faced the problem of correct positioning of EMG sensors, and then we, how to say, found doctors in order to resolve this problem.
Yeah, so we have some collaboration here with the neuroscience department, and they were helping, so Professor Miguel, he was helping us to somehow locate the sensors. No, however, the first part of the research, when we put the many sensors in the palm, was with this goal, not to explore more the palm area of the users, because in the literature we found like how many receptors are in the palm, but not like how to use these sensors in the application of wearable devices. No? So I think that's why it's a big field that we can explore, no? And together with the neuroscience department or neuroscience doctors, no? to continue it.
Yeah, and the second question is, so obviously that you have lots of results that can be used in industry or startup companies. So did you manage to license some results to pilot them with big names? So could you comment on this?
Yeah, no, in this part of the work, I didn't manage to make some studies in the industry. However, so in the laboratory we have many visitors. No? Every week we have some companies or some people that come in to see our technology. One of the demonstrations is always this teleoperation of the robot through Zoom, and they are very interested on this type of technology. The use of the collaborative robots, industrial robots, now is very, very used in the industry. This human-robot interaction, no? Like how we can take advantage of the dexterity of the humans and the precision of the robots. So in the future, I hope to arrive in the industry and to give some feedback from them.
All right, thank you. I'm done.
You're done? Okay, thank you very much. Andrea, are you satisfied with the answers, the comments that were added to the modification to the thesis that you suggested for your comments?
Yes, I'm fine with it, thank you.
Okay, thank you very much. Okay, we'll now go to Professor Pedlachikova for comments and questions. Please, Tatiana.
Yeah, thank you very much for this work and for your nice presentation. And I would like to congratulate you with your results that you have obtained. I have a question that is related to my professional interests. I'm very curious. So you use some kinematic models, right, that you showed on slides to describe motions. But looking to your thesis and presentation, they're deterministic models. But in reality, can this deterministic model be fully correct to describe some motion? Or it may be better to introduce some level of noise to model, and it would make so you will work with stochastic model, and it will make your model more flexible, but of course you need to know statistical characteristics of this noise. What do you think about it?
Yes, thank you. Thank you very much for the question, observation. So to be honest, I didn't implement this part in the research. In the future, I would like to implement this part. I can say, like, in theory, everything is very clear, no? So when we make the mathematics in the computer, but after when we pass this information to the real robotic systems, is a very good try, like, to increase the noise and to determine better the movement of the robot described by the kinematics. No? For example, this method I mentioned in the work, we should limit it, no? Because we have many positions of the robots or the motors to arrive to the position, no? But we should limit them to only the ones that we want in the robotic system. Thank you for the comment.
Yeah, thank you. So you have plans to try this?
Now I have plans to try, yes.
Yeah.
Thank you.
If you would like to try it in future, I would be interested to see results and maybe help you with the identification of these noise statistics. This is my personal interest, and we can. This is an extremely complex topic, but maybe we can try. Yeah. Thank you.
Yes, thank you very much.
Thank you very much. Yep. Are you done with? Okay, thank you very much. Professor Pedlachikova, are you satisfied with the modification and comments?
Yes, I am. Thank you.
Okay, thank you very much. Well, for myself, thank you very much, Miguel, for the excellent thesis and a lot of research work and many cases that you presented. But it's very, very interesting and varied. What do you think is the most promising commercial avenue for in all the things that you tried? What do you think is the most mature, that if you had a opportunity, where would you invest? Where would you go?
So, thank you for your comment, for your this is comment about my work. I think in this part, the teleoperation now is very, very important. No? How we can teleoperate the robots in another environment to reproduce the movement of the users, no? of the person. This to take advantage of the dexterity. Now the lack of the specialist, no? That can be located in another part of the world, and to make some work in the place that we need to make this movement. So I think the development of this type of systems for increase the safety, for example, to make some analysis of dangerous substances can be very promising, to move so the user has to make this movement, and not only for telemanipulation of these tiny objects, but maybe healthcare is a very, very big market. No? Now many people need the robots together, for example, to make some exercises with the body, to perform some rehabilitation, for example. No? So we can use these teleoperation systems to give the right positions of the users that need the assistance of a person, the real person, together with him, using the robotic systems. Another field that is growing very, very fast now is the support of the robotic systems in the house. No? So how we can teach the robots to make very simple stuff that we think that are solved by the robotics, but it's not, like clean the dishes, or open a cassette, or to fold the clothing or something like this. So we can, using these teleoperating systems, to teach the robot to perform these actions, to after like this teaching by demonstration, to give the human skills to the robot, and after learn and to reproduce in the market.
Okay, thank you. I saw in your supplementary slide that you have a reference diagram or an impact diagram, and you know that I'm interested into this to see, but did you update this, or and which part of your thesis is it covering, of your research work?
Yes, I can show.
Can you? Yeah, I would like to see it just to for my benefit.
Actually, this tool, I can comment. This tool was very very useful for me in the research. So we took the course with you, like how to develop the research, and helped me to identify, especially, where are these, especially these three questions, no?
Okay. So here the reference diagram, yes.
Maybe so I didn't modify this slide for this presentation, but this is the diagram, no? That I have here. In one part, the teleoperation system, teleexistence, so user immersion using haptic feedback. We have especially till now the visual feedback only in the teleoperation systems, and some haptic devices using for the teleoperation. And in the remote environment, we have the human-robot interaction, the human-robot distance, the number of collisions, the operation time, the human tracking system. So after the work was focused in these parts, first, how we provide the stimulation in the user, so how we can receive the information from the sensors and to transform in some data that the user is capable to sense. After the development of the tactile feedback, tactile device, multi-contact tactile device, after the multi-user teleoperation system, and to apply some haptic stimuli in the forearm of the users.
Did you identify the measurable success factors? But I guess you have many. If I look at your thesis,
yes,
they are spread in different parts of the diagram, or yeah, I would say. Okay, thank you very much. Quite interesting. And I'm satisfied also to the answer. You modified question 3. I think that you covered so wide that it's, thank you very much for all your work. So now we will go to questions from the audience, if there are any. Are there some questions? Or online? I see there is as I saw, Elena, there is a comment in Zoom. Is it for a question?
Yes, it was my call for questions from audience online.
Okay.
But I can't see any questions.
Okay. Any questions for the audience here? Sure, come to the microphone. So that they, okay, yes.
Yeah, thank you so much. So I was really proud to work with Miguel. I was like really supervised by him with Professor Dimitri, and I know that he already started a startup somehow with the rehabilitation. So do you think that the haptic devices that you developed can be implemented somehow with the rehabilitation? I know you have sensors here to measure the signals from the head, but do you think that it might be applied also, since like this is also might be related to the startup that he's starting? I hope my question was clear. No?
Thank you for the comment. Yes, we started a startup for rehabilitation of the people, but especially for people that suffer a stroke. No? So these people cannot move. So we are using EEG information from the brain to move and make the rehabilitation according to the points that the people are thinking about. No, they cannot speak. They are sitting in the bed, and according to the information on the brain, we are moving the robot to different positions. This is the global vision of the startup. We are here trying to implement some haptic feedback as well, but this was proposed to from the neuroscience department to give in the spinal, no, in the back of the users. However, yes, I think so because we have different parts of the teaching, no. First, the user is, so the patient is in the bed, and after the expert comes and performs the movement to save in the robot. This movement, for example, of the expert to make the rehabilitation, so the first movement, can be done by teleoperation. You know? So in future, maybe this can be done by teleoperation, and the haptic feedback can be in the operator, no? In the expert that is performing this movement. So yes, I hope in the future we can implement this work too in this field. Thank you.
Thank you very much. Yes, go ahead, Leg.
First of all, thank you, Miguel, for the beautiful presentation. I was happy to work with you all these 4 years, and I would like to ask you a question to specialists in haptics. What do you think is the biggest milestone for us as users as a future users of haptic devices, to haptic devices become finally usable, and what is the key technology there is lack right now for us to use it? Like for example, when computers was not affordable for everyone, the transistors emerged and everyone started to use it at home and in the phones. What do you think? What is this key technology for haptic devices when we will use it in maybe 20 years every day at homes?
Thank you for your comment, for the question. I think it's a key question that sometimes we don't realize how we are using even now the haptic feedback. No, like we think that are devices that in the future, yes, this one for the palm, maybe yes will be not in some months, no, but haptics is implemented now in many devices. No, for example, in the phone, no, we have some vibration and we feel this haptic sensation that gives us some information that we are receiving some call or whatever. No, the watch, that makes some vibration. We know that someone is calling, no, or when we I don't know, we are running, that you should slow down because your heart is too strong. So these technologies we are now using. However, one of the limitations too, for example, for the teleoperation in the surgeries could be the internet. If we implemented some faster internet, we can send the data more in real time, because these systems are very dangerous. So we are talking about the surgeries of people. The same for the space. We need this information to be more fast, precise, and stable. Because sometimes now we can, yes, be connected, but after there are some lags. So yes, I can mention this part. After, yes, the implementation of new materials, for example, the development of this resistance material that can deform with the high voltage, for example, can be some applications. Soft robotics as well, to develop the soft robotics in a better way, to don't need many pumps and this stuff that we need in this moment. But yes, the field is very big, and I hope we will arrive to the like more spread use of these devices for example, virtual reality or some teleconferencing. That's the main focus. So teleoperation, virtual reality, and training. Thank you.
Okay, thank you very much. I think that we'll stop there for questions. Thank you very much. And we'll now give...
I'm sorry, Professor Fortin. We have question from audience online.
Okay, good.
From user Juan Heredia. So maybe if you could just turn on the sound and read your question aloud.
Yes.
Hello, may you hear me? I don't know if you can hear me.
Yes, we can hear you well.
Yeah, so first I want to congratulate Miguel for his wonderful presentation and also his dissertation. And I want to ask one question. It's about the future Industry 5.0. In Industry 5.0, humans and robots play an important role and will collaborate together. So I want to know, what do you think about the role of haptics in Industry 4.0? And how does your work contribute to this Industry 4.0? Did you hear me well?
Thank you. Yes. Thank you for your question. It's a pleasure that you're connected too. Yes, so the application of haptics in Industry 4.0 can be like, for example, in this part. Like in the industry, we have a lot of sound, and sometimes not the visual, so the workers are very distracted because they have to be concentrated in the work and they cannot see something more around them. The noise that is too, that we cannot have many sound feedback, for example, and haptics we can use to give this information to the users. For example, in the work that we develop together too, to give that haptic feedback to inform about some difficulties in the system, that you're very close to the robot, or we want to decrease, for example, the time of the operation. So in that case, it's not only the robot that is making the collision avoidance of the user, but the user is making this collision avoidance of the robot as well. So that together can arrive to reduce the time and to increase the information that we can provide to different systems in the Industry 4.0. I think this is a very, very good field too, and we should continue studying this part. After not only having to, yes, of course, the security of the users is very important, but the same, the consuming of energy of the robots. So we can reduce the consuming of the energy in the big industries if we reduce the time, or we implement some collision avoidance algorithms that makes the path like more energetically safe. Or thank you.
Thank you very much for your answer, and you did a wonderful work. I just want to congratulate for all the effort that you did during these 4 years.
Thank you.
Thank you very much. And maybe I have a small comment here. I think the impact of your work of haptics is, to me, more related to Industry 5.0 than 4, because in 5, human-centric automation or industrial integration is very important, and I think haptics is one of the key elements of of this. So definitely a strong contribution of your work, or this whole field is key for the future of Industry 5.0. And of course, we could talk about this for a while, but it's very, very interesting. Thank you. All right. Now time to go to the supervisor and his comments. Please, Dimitri.
Yeah, thank you. First of all, I'm very impressed by the work of Miguel Altamirano Cabrera, with whom I'm working for almost 8 years, right, starting from master degree. First of all, I would like to say my big gratitude to the chair of the committee, Professor Clement Fortin, and to our members of international committee who found the time, and thanks to their professional comments, Miguel could improve the thesis as well as Professor Navarra Alarcon from the Hong Kong University, Polytechnical University, and also Professor of Tsinghua University, Ho Chan Zhao. So thank you so much for being the members of PhD committee. And sure, I would like to say my gratitude to Andrei Somov, professor who is one of the top experts in Russia in the field of IT, and Professor Tatiana Podlachikova, who is the director of the Center for Digital Engineering and a great expert in Kalman filtering and space weather. So as to the work of Miguel, I really impressed by his achievements, not only from scientific point of view, but also from the point of view of providing the high quality technology and very complex technology. So as a result of his work, he published 24 papers. To my knowledge, is a world record in the field of haptics, and it's really a big work was done during recent 4 years. So, and one of these publications are A-star ranking and Q1 journals. So he developed not just a part of the system, right? Only haptic feedback. He developed a new type of teleoperation system. So basically, he worked on multi-contact haptic feedback to achieve the high quality immersion in the remote space. He did the CNN-based recognition of the gestures to achieve the very intuitive way of control of the robot through distance. And definitely one of his strong contribution was also to achieve the safety for the remote place. Because this work that we do in teleoperation and it potentially can harm human can be the limitation for the future Industry 5.0. So for this, he developed a collision avoidance system, right? And human recognition to provide the safe teleoperation. So this is really very impressive work. Also, I would like to say that application of this system is definitely could considerably improve the quality of safety, but also do kind of new way of communication and interaction with the robots in Industry 5.0 and virtual reality, right? These two fields of study now benefiting from haptics. Many companies now investing in this development, many universities appears, and the next conference, EuroHaptics, where the Miguel also will present in the paper, is actually will be conducted in Lille, who is the guardian of the multi-touch, huge project, multi-touch Horizon 2020. And from the scientific point of view, the future contribution, not only contribution about study of the perception, this is very strong, study of how we can manipulate the object, study how we can render the object on the palm, very important now is a very hot topic, is the imitation learning. And most of the university like Stanford and companies like Google DeepMind currently are focusing on how to teach robots to perform a complex, sophisticated task like cooking, like folding of the closure, and so on. And having this high dexterous telemanipulation, and high dexterous, high quality haptic feedback can potentially considerably improve the teaching opportunity for providing the human-like behavior from getting the expertise from human, including the inverse reinforcement learning, including the behavior cloning, and so on. The approaches that just recently emerged, and they're done through teleoperation or control of the robot with different modalities. And finally, I would like to say that Miguel has a great personality. He is a very kind person, very supportive. He co-supervised many master students, and I'm very proud that today we have the Juan Heredia, who joined our meeting and gave the question. Now he is professor at South Denmark University, and they worked together with Miguel several years ago. And thanks to Miguel, many good expert appears in Russia and abroad in the field of haptics, control, and collaborative robots. So thank you, Miguel, for working with the students, for doing a great science, great research, and I'm sure that if we continue to work together in this field, we achieve a new level in this field, and we represent Skoltech and the top conferences, and we'll do a great interaction with industry and startups. Thank you for your amazing presentation. I fully support Miguel for the PhD position, PhD degree based on his scientific achievements. Thank you so much.
Thank you very much, Professor Teterogu. It's now time for the closed deliberation. I will ask the candidate and all the guests to leave the room, and we will deliberate with the jury members only.
Dear audience online, you're most welcome to stay connected. We will now open a separate breakout room only for the jury members. They will receive the invitation shortly, and all the audience is most welcome just to stay connected to the main session of the meeting. Once the jury is ready with their decision, we will be back for the announcement of the result.
Dear Miguel, the jury member has voted and decided the defense pass as is, and congratulations for the obtention of your PhD degree. Thank you. Very good. Thank you very much for the practice. Thank you very much for everybody for being with us. Thank you very much for the external jury members. We really appreciated your work and your contribution to this academic defense, and I thank everyone, the supervisor, the candidate, the jury, and the attendants, the people that came and listened. So thank you very much for all, and have a great day. And we're looking forward to see you, and you're always welcome to come to see us here. Bye-bye. Yes.
I want to thank you too, especially the Professor Dimitri, Professor Clement, Professor Tatiana, Professor Andrei, for the support, for helping me to improve my thesis. Professor David too is connected, and all the supporters of the thesis, especially to my family. ¿No? Muchas gracias a mi familia. Yes, especially thank you to Skoltech, ¿no? For giving me this opportunity to start with the master's studies, and after to continue with the PhD, and now to continue with the research. Yes, very thankful for all the students that passed too in my team. Very good to see Juan, no, that was the student in my team, and now he's the professor, as the professor mentioned. And yes, so I was thinking this day will not come, no, but finally arrived. So thank you very much.